In this video, I'll go through a Simulink model of the Boost PFC, and the goal is that you will get a better understanding of how the Boost PFC works. So I'll just go through all of the scopes that you see here, and I will explain along the way. So first we have the source voltage, which is the voltage that goes into the PFC, and this comes from the grid, so it's sinusoidal. And then we have the source current, which is the current pulled out from the grid and into the converter. So you can see that it has a lot of ripple, so it would be a good idea to add a filter between the converter and the grid in order to reduce the ripple or remove it completely. And then we have the full bridge. These are just diodes. I just use switches without a gate signal, so then it operates as diodes. And now the full bridge basically rectifies the current. So you can see that the current is now the absolute value of a sinusoidal signal with also ripple. And then the voltage has the same waveform, but you can see that there is a lot of ripple in the zero crossing, and that is because the current changes direction in this zero crossing because of the ripple. And then we have the boost converter, so it's basically controlled by this switch here, which comes from the control circuit. So, and then we have a diode here. So the control circuit is basically a voltage controller, then followed by a current controller, and then a PWM to decide the PWM that goes into the switch. So I assume that you have an understanding of the boost converter, but I will just go through quickly the controller here. So first we find the error of the voltage in order to, and it's fed into a PI controller, and then we also add a feed forward to get the peak of the reference current that we want to have. And then we oscillate by multiplying with the waveform of the source voltage. So we multiply the peak with the waveform of the source voltage, or it's just a sinusoidal signal, and then we get the reference current that we want to have for the source current. But we take the absolute value of that because the input of the boost converter is this current and not the source current, which is sinusoidal. So this is the absolute value of the sinusoidal. So that's why the reference current is also the absolute value of a sinusoidal signal. And then we have the current controller. This is a lot faster. You saw that the voltage controller was very slow. You can see that it moves slowly, and that is intentional. And then we have the current controller, which is a lot faster. So basically how the current controller works is that we have a duty cycle, which is 1 minus the absolute value of the source voltage divided by the output voltage. So that is what the feed forward does here. But the model is not perfect, so we need to correct for the error, and that we do with a PI controller. So you can see that the duty cycle is basically the current flipped and scaled. So this is the current. So if you just flip it and scale it, you will get the duty cycle. And then we add a saturation because the duty cycle is defined between 0 and 1. And after that, we have a PWM just to convert to the gate signal. And now we have the current going out of the boost converter would look something like this. So it would go, operate between 0 and then the current going through the inductor. So if we just zoom in here, so you can see that when the MOSFET here, or the switch is on, all of the current goes through the switch. So the current going through the diode is 0. While when it's off, all of the current going through the inductor goes through the diode, as you can see here. And now the blue one here is just the current going into the load. So actually, if you take the average of this blue one, you will actually get a sinusoidal signal. So I just did this with a filter, you can see that the current going out of the boost converter is sinusoidal with an offset. And you can see that the average is the current going into the load. And this is the case because we're in a steady state. Now you can see that the difference between these two currents is the current going into the capacitor. So this means that we should have a ripple of the voltage, because if you integrate the capacitor current, you will get the voltage of the capacitor. And this is reflected in the output voltage. You can see that it has a ripple, which is equal to the integral of this current minus this current. And then also multiply by the capacitance. So that is basically how Boost PFC works. So you can see the main results here, or the most important signals. So you can see that the current becomes sinusoidal, but with some ripple. And then we have the voltage going in has the same waveform as the current, which is the goal of the Boost PFC. And here we have the duty cycle and also the output voltage.